Gravity Revisited and planetary motion going to be the topic of this lesson in my brand new general physics playlist, which will eventually cover a full year of university algebra-based physics. Now we're bringing this up in the context of circular motion because oftentimes we're talking about planetary motion in the context of orbits, like planets orbiting the sun or moons orbiting the planets, or satellites orbiting planets, things of this sort. Now we won't be exclusively talking about it in this lesson in the context of circular motion, but that's why it's appearing here. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So when we brought up gravity a few chapters ago in the context of Newton's laws of motion, we defined an object's weight most commonly as simply mass times gravity, where gravity was looked at as a constant 9.8 meters per second squared. Well, this belies the fact that you're applying the situation only to the surface of the Earth, which granted is, the most common experience that any of us are going to have and stuff like that, and real common in Newton's laws of motion problems. So, but in the big, grander scheme of the universe, this is a very special case. And so we also brought the more universal definition for the force due to gravity. So it is gravitational constant times the mass of one body times the mass of the second body, all over the distance of separation squared. And so we can see that the force due to gravity was proportional to either of the two masses experiencing this force, this attractive force due to gravity, but it was inversely proportional to the square of the distance of separation. It's one of our inverse square laws. So if you double either mass, that force of gravity doubles. If you double them both, the force of gravity quadruples. If you double the distance of separation, the force of gravity goes down, but not by a factor of 2, by a factor of 4, inversely proportional to the square of the distance of separation. Okay. After dealing with some Newton's laws of motion, we started talking about work and energy, and we brought up the idea of gravitational potential energy. And the formula we used, again, implied a special case, only applying to the surface of the Earth, and it was mass times gravity times the height. And there was a couple things wrong with this. One, and I shouldn't say wrong with it, there was a couple special things about it. So one, it was defined in the context of only applying to the surface of the Earth. But two, the height was chosen relative to some reference zero height. And that might have been, the lowest level in the problem, which might be the top of the building, or it might be ground level. But what if all of a sudden you go into the Grand Canyon and you go lower, and all of a sudden you got to define a new zero height and things of this sort? Well, in the context here, so the distance of separation is always from center of mass to center of mass. And so for me right now on the surface of the Earth, it'd be from my center of mass to the center of the Earth. And so, trying to define a height relative to some reference zero height isn't really going to work in this case. If we want to come up with now some universal formula for the gravitational potential energy, we can't just have some sort of arbitrary height as reference to some reference zero height that we choose. We need something that's a little more universal than that. And so turns out we do have a definition for potential energy and gravitational potential energy that's more universal. So it looks like this, and it looks somewhat similar to what we got for force here and stuff like that. And it turns out that this potential energy is equal to the negative of the work in moving an object in some sort of universal gravity and stuff like that. So, and you can get it actually and derive it using a little bit of calculus to calculate that work. Well, obviously we're not doing any calculus in this class, but this is a formula you're now on the hook for gravitational potential energy in a universal sense. Again, if you're near the surface of the Earth, there's nothing wrong with this formula. So, but if you're not near the surface of the Earth, this is now the universal formula for the potential energy due to gravity. So the rest of this lesson, we're going to be talking about planetary motion and doing relevant calculations. And one of the terms that's going to come up is called escape speed, sometimes called escape velocity. So, and now that we've got a more universal form for gravitational potential energy, we can derive an expression for this escape speed. But the idea is the escape speed is the minimum speed something must be shot off of a planet with in order to escape the gravitational pull of that planet. We can kind of calculate this thing. Like I said, we can derive an expression for it. So, and we're going to use conservation of mechanical energy to pull this off. And so we've said conservation of mechanical energy means the total mechanical energy at any point in time is going to be the same. Well, the argument we're going to make is that it's actually going to add up to 0 all the time. So we'll see why this is, but the idea is that, let's say we throw this marker up in the air, and I throw it up in the air. Well, at the top of its trajectory, that's where its velocity reaches 0. And so as it's moving up, its potential energy is increasing, but its kinetic energy is decreasing. And when it reaches that apex where the velocity is 0, its kinetic energy has gone to 0, and its potential energy is now at a maximum. So that's what's going to happen here as well. As this thing is shooting off the planet, its potential energy is going to be going up. And it's going to reach a maximum when it gets infinitely far away from that planet. That's going to seem a little bit strange. So if we take a look at what potential energy and kinetic energy are, so 1/2 mv squared for kinetic energy, and then our new definition for potential, instead of putting plus and negative, I'm just going to subtract. But g m1 m2 over r squared, oh, just over r, my bad, equals 0. And so here's the deal. When we reach infinitely far away from that planet, that means the distance of separation is infinity. When you divide by infinity, you get 0. So as r approaches infinity, our potential energy is going to be approaching 0. Well, we just said, just like this marker, as it goes up and up further away from the planet, its potential energy increases. But in this case, what's going to be weird, though, is that it's going to increase to a maximum of 0. And so it turns out the potential energy is going to be negative. And the further it gets away from the planet, it's going to get less and less negative until it gets infinitely far away from that planet and reaches 0. So 0 is kind of the ceiling on gravitational potential energy here. And that just seems a little bit weird, but there's nothing that says that potential energy can't be negative, and it totally is. And we'll see that this is totally true for attractive forces in other contexts as well. All right, so in this case, the idea is that we're going to shoot this with the minimum velocity necessary to get to that infinite distance. And it's going to be losing kinetic energy the whole time until it just reaches the point where it's got 0 kinetic energy. Okay, and so we can envision a situation again where it's infinitely far away and your kinetic energy is 0 at that point and your potential energy is 0 at that point. And so the total between these two adds up to 0. And again, for the conservation of mechanical energy to hold true, it means that the total mechanical energy has to add up to 0 through all points of the motion, including right when this projectile is fired off the planet. Well, right when it's fired off the planet, so that's when you've got some kinetic energy and you've got negative potential energy, but they still add up to 0, and we can kind of rearrange this equation. So 1/2 mv squared equals g m1 m2 over r. So now keep in mind the m1 and m2 here. In this case, let's say we're shooting this off the Earth. Well, one of these masses is the same mass over here that's got kinetic energy, so I'm just going to call that m. And the other one is going to be the mass of the Earth, which it's common to write with a capital M-E. But notice the mass of this projectile just falls out of the equation. So we're going to solve for v here in a little bit. So v squared is going to equal, move the 2 to the other side, so 2g me over r, and then we'll take the square root of both sides. And this escape speed or escape velocity is equal to the square root of 2 times the gravitational constant times the mass of the Earth divided by r. And in this case, if it's being fired off the surface of the Earth, then this r here would be the radius of the Earth as well. Cool. And again, here I've done it for the Earth, but you can put any planetary object in there. You could put, if you knew the mass and the radius of Mercury, you could figure out what the escape velocity off Mercury would be and things of this sort. One thing to note is this completely ignores any form of air resistance. It is only evaluating this in the context of gravity. The real escape speed off any planet that's got an atmosphere is going to be greater than this. So, but purely from a gravitational sense, this is what it is. And this is the formula, and you may be doing some plugging and chugging. So, and on the study guide, I put that formula for it, but we just derived it as well. And again, we just derived it from first principles, saying that the total mechanical energy must be 0. So first question here says, what is the weight of a 75.0 kilogram man on the surface of the Earth? And then second question, similar, what is his weight at an altitude of 260.0 kilometers above the Earth? And then the mass of the Earth and the radius of the Earth are provided to help us calculate this. Well, surface of the Earth life is good. We can just say weight equals mg and do some simple calculation here. So 75.0 kilograms, 9.8 meters per second squared. And we can see he's just going to be shy of 750 newtons here. So, all right, so 75 times 9.8 is 735 newtons. Okay, so that's the first half. Same way we would have calculated weight back when we were discussing Newton's laws of motion. So as long as you knew the surface of the Earth, nice simple formula. But what if we're now at an altitude of 260 kilometers above the Earth? And so in the first case, he's on the surface of the Earth. But in the second case, he's now above the Earth. And so we're going to find out that when we go to calculate the force due to gravity here, G m1 m2 over r squared, when we go to calculate r, that's going to be his distance from the center of the Earth. And so that's going to include the radius of the Earth, but it's also going to include his altitude above the Earth as well, the sum of those two. All right, so in this case, force equals gravitational constant, 6.67 times 10 to the negative 11. That's Newton meters squared per kilogram squared, times his mass, 75.0 kilograms, times the mass of the Earth given in the problem as 5.98 times 10 to the 24th kilograms. And then divided by the distance of separation squared, which in this case is going to be the radius of the Earth provided as 6.38 times 10 to the 6th meters, SI units, plus an additional 260 kilometers or 260,000 meters. And then we got to square that sum. So if we just use the radius of the Earth, we're going to get this wrong. In fact, if you just use the radius of the Earth, you'd get 735 newtons again. But now at this altitude, we should expect his weight to be less. Now it turns out that 260 kilometers, that's a common orbit for a spacecraft or a satellite or something like that. And you might be like, oh, he's in outer space on an orbit. He should feel weightless. Yes and no. He should feel weightless, but he won't actually be weightless, as we'll see. Let's perform the calculation here. And notice the bottom here, if you were going to try and add this together, you could put these both in scientific notation and make this like 0.26 times 10 to the 6th, so that they both have the same power before adding them. But obviously, you can just let your calculator do all the work for you. So 6.67 times 10 to the negative 11 times 75 times 5.98. Oop, that's 8998 times 10 to the 24th divided by, get my parentheses in there, 6.38 times 10 to the 6th plus 260,000. And then don't forget to square that denominator as well. And here we're going to get 678.5, so which rounds up to 679 newtons. Make sure I've got all those numbers in there. So many plugged in there. So 6.67 10 to the 11, 75, 5.98 times 10 to the 24th, divided by 6.38 times 10 to the 6th, plus 260,000. Lovely. All right, so if you look at this here, this is a little bit of a strange result. Because again, he's in outer space, in orbit, and he still has a weight. In fact, his weight is like somewhere in the ballpark of like 90% of what it was at the surface of the Earth. And that's contrary to kind of what we envision being out in orbit and space is like. It should feel weightless. Well, you do feel weightless, but you're not actually weightless. Your weight isn't zero. You actually still feel the majority of the weight, if you will, the force due to gravity that you would, I shouldn't say you feel it, but you have the majority of the weight you would at the surface of the Earth, even at an altitude of 260 kilometers above the Earth. So what's the deal here? Well, right now I can feel my weight, and the way I feel my weight is by the ground pushing back at me. There's a normal force, the ground is pushing back, and it's that normal force, this contact force, that helps me feel it. You might be like, well, Chad, if I jumped out of an airplane and went skydiving, I'd totally feel gravity. You're right, but you'd only feel it because of the wind. If you could close your eyes, you're right, you'd totally feel it because of the wind. The wind's another contact force that would help you feel the gravity that's pulling you in the opposite direction. But let's say you jumped out of an airplane. Now, let's say it's not an airplane. Let's say it's a space plane because you're in outer space now. So where there was no air, you actually wouldn't feel gravity. You'd be falling. And you'd be in free fall. But if you closed your eyes, you actually couldn't feel that you were falling. So kind of a weird thing. And unless you have a contact force of something you're coming in contact with, like the wind or the ground or something, you need something to help you feel a non-contact force like gravity. So that's kind of the deal here. And so as long as you're in this uniform circular motion of orbit around the Earth, in some sense you're in free fall. So obviously you're not necessarily getting closer to the Earth in a stable orbit, but you're experiencing still, you have a weight that you're still experiencing. You just can't feel it without a corresponding contrary contact force. All right, so notice you'd actually have to be infinitely far away from the Earth for this force to go down to zero. This denominator would have to go up towards infinity for you to actually feel zero force due to gravity. So again, if this is a little bit of a funny result, was to me too, first time I did such a calculation. So now that we've dealt with a common orbit altitude of 260 meters, we're now going to say, what speed would a satellite need to have in order to be in a stable circular orbit around the Earth at an altitude of 260.0 kilometers? So in this case, again, envision some guy in a spacecraft, or in this case, a satellite going around the Earth. And he's undergoing uniform circular motion. And uniform circular motion, sum of the forces equals mv squared over r. So your centripetal force in this case. Well, and in this case, it's gravity, right? And gravity is g m1 m2 over r squared. And that force equals, it's the only force, so the sum of the forces of mv squared over r. Okay, so one of these masses, m1 and m2, is the mass of the satellite in question here, and I'm just going to call that m, and it's going to cancel. The other one is going to be the mass of the Earth, which we'll write as me. So, and then r here is the distance of separation. Again, that distance of separation is going to be the distance, not just the radius of the Earth, but the radius of the Earth plus that altitude again. Well, one of these r's cancels, and we're just going to be left with v equaling the square root of g times the mass of the Earth all over r. All right, we can do some plugging and chugging. So g is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times mass of the Earth, 5.98 times 10 to the 24th kilograms, given yet again in the question, all divided by r, and once again, it's going to be that radius of the Earth plus, so the altitude that he's at, and that radius of the Earth was 6.38 times 10 to the 6th meters plus, and again, 260 kilometers is 260,000 meters. Get everything in SI units. But we don't square it in this case, but we will take a square root of the whole thing to get our velocity here. And let's see what this needs to be. All right, so 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th divided by parentheses 6.38 times 10 to the 6th plus 260,000 in my parentheses, and then we'll take the square root of that answer. 7,750 that's going to be meters per second. If we look back at the question, it looks like we actually want 4 sig figs. Should I take this out one further? And it would actually be 7,750.49, which means I'll leave this rounded down. And whether I put that over the 0, which again is not my favorite, but I'd make this 7.750 times 10 to the 3rd meters per second. All right, next question says, what is the escape speed of a rocket leaving the Earth? Ignore air resistance. Gives you the gravitational constant, so the mass of the Earth and the radius of the Earth. And from here, it's simple plug and chug. We derived this earlier, so simple plug and chug. All right, same radius here as we've been using, 6.38 times 10 to the 6th meters. All right, we'll let the calculator do our heavy lifting once again. So 2 times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th divided by 6.38 times 10 to the 6th equals, and we'll take the square root of that answer. We're going to get 11,181.966. And in this case, we want to round that to, looks like, I guess we're rounded to 3 sig figs. All the other numbers are data what was provided, which we usually think is, considered infinite oftentimes, but we'll round it to 3 sig figs just like our radius of the Earth here, which is going to get us 11,200 meters per second. So the last part of this lesson is going to be devoted to Kepler's laws of planetary motion. And it's common for this to be omitted from the curriculum. So if it has been omitted in your particular class, then by all means, skip straight ahead to the next video from here. But for the rest of you, Kepler's laws of planetary motion, there are 3 laws. Kind of got to have a little bit of an idea of what they are, and you might have even a calculation involved in the last one. So the first law just says that planets have elliptical orbits with the sun as one of the focal points. So if you look, the proper shape of the orbits for the planets is elliptical. Now, they're fairly circular, it turns out, but for the planets in our solar system, it is proper to say that they are an ellipse rather than a perfect circle. Now, if you looked at, say, comets and asteroids and stuff like that that go around the sun, they are much more elliptical than those of the planets. The planets are fairly circular in comparison, but again, it's proper to say that they're elliptical. Second law says the line between the sun and a planet sweeps out equal areas in equal intervals of time, and this needs a little bit of explanation with the diagram. So the idea behind about what we're to discuss here is this. If I drop this marker and let it go to the ground, as it moves on down, its potential energy is decreasing, its kinetic energy is increasing. And the closer it gets to the Earth, which it's attracted to by gravity, so the faster its velocity. Well, in this case, similar, but in this case it's regard to the sun. So as an object gets closer and closer to the sun, it has less potential energy and more kinetic energy, is moving faster. And so the object undergoing this elliptical orbit around the sun is moving faster on this side and slower on this side. Faster when it's closer to the sun, slower when it's further away from the sun. And so what ultimately Kepler said is, so say we got one position of this object in orbit here and another position here. So, and there's a passage of time to get from here to here, delta t. Well, he looked at that and said, hey, let's create a sweep of area in this orbit here. So, and if you look at exactly the same passage of time over on the far end of the orbit, let's say, so, and that might just be from, here to here in the orbit. And notice you might be like, well, that's the same amount of time? So that would be my argument. That was Kepler's argument. So, but again, because the object is moving slower out here, it doesn't travel as far in the same given interval of time. But what he said is if you draw the sweep out now, the same kind of a sweep, what you'll find is that the amount of area covered here is exactly equal to the amount of area covered right here. And finally, Kepler's third law is really more of an equation or a relation, as it turns out. So ultimately, he said that the period of the orbit squared is going to be proportional to the distance of separation, or the radius of the orbit cubed, or at least this is how we're going to look at it. So again, he looked at orbits as being more elliptical, and instead of this average distance to the sun, he looked at the length of the semi-major axis of the ellipse, things of the sort. But again, we're going to approximate the orbits of the planets in our solar system as being fairly circular, and therefore look at this as the radius of the orbit, the average distance to the sun. All right, if you look at the proportionality, all these are constants in here. 4 is a constant, pi is a constant, g is a constant, and the mass of the sun is a constant. And so there's that relation. So some of you, maybe all you're on the hook for is realizing that the period squared is proportional to the average distance cubed. So for others, you might have to actually do a calculation with this. So we're going to actually set up the derivation for this and then do a calculation with it as well. We'll definitely need a little more room here. All right, so here is the circular orbit of a planet around the sun that we're envisioning. So, and in this case, it's undergoing uniform circular motion. There is a gravity pulling it towards the sun, and that is the nature of the centripetal force here. And so just like we do in the problems we've done earlier in the chapter, the sum of the forces equals mv squared over r. In this case, those forces only comprise gravity, and so that's g m1 m2 over r squared equals mv squared over r. Now, a couple things here. So in our case, one of these m's is the mass of the planet, and one of them is the mass of the sun. It's customary to capitalize the mass of the sun. So, but this m over here is the one undergoing uniform circular motion, experiencing the centripetal force, and that's the mass of the planet as well. And that mass of the planet is going to fall out of this equation, and one of these r's is going to fall out of the equation as well. And so here we're going to be left with g times the mass of the sun over r equals v squared. And what we're going to do is we're going to come up with an expression of the velocity here in terms of t, the period of an orbit. And so what we can look here, so velocity is equal to distance over time with a capital T here. So, and that's the time period of one orbit if we can get the distance of one orbit as well. One full orbit is going to be a distance of a full circle. That's the circumference of a circle, which is 2 pi r, and the time of that orbit we're just calling capital T. And now we have an expression for the velocity we can substitute in terms of, so the radius of the orbit as well as the time of one orbit. So we're going to have 2 pi r over t, and we'll square it, expand this out a couple more times here. So GMS over r equals 4 pi squared r squared over t squared. We'll move the t squared over to this side, get it all by itself. So, and then on the other side, we can see we're going to have a 4 pi squared over GMS, and we multiply by another r, times r cubed, and we've now derived our expression for Kepler's third law, and now we can do a calculation with it. So the question says, what would be the period of orbit in days around the sun for a planet with an average distance of 150 million kilometers from the sun? And once again, the mass of the sun is provided. And it's just plug and chug at this point. Some of you may be on the hook for this. I highly doubt you're gonna have to memorize this equation, but I can't guarantee it. Some professors are pretty litigious in making sure you memorize everything imaginable. So, but most of you probably not the case. But you might have to be able to use it if provided it, and that's what we're gonna do here. All right, so there's Kepler's third law rewritten, and we're just gonna insert all the variables and solve for the period here. So t squared equals 4 times pi squared all over 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So mass of the sun's given as 1.989 times 10 to the 30th kilograms. And then we got to multiply by the radius or average distance of the sun cubed. So here's the tricky part. It's given as 150 million kilometers. That's 150 million, but that's in kilometers. SI unit should be meters. So we got to multiply by another 1,000. It's 150 billion meters cubed. And we're definitely going to let our calculator do the heavy lifting for us here. All right, so lots of places to screw this one up. So 4 times pi squared divided by parentheses 6.67 times 10 to the negative 11 times 1.989 times 10 to the 30th, and my parentheses, times 150,000,000,000,000 cubed gets me a number, and then we'll take the square root of that number. All right, let's write this out. So t equals 3.1691037 seconds. So, but the question wanted the number of days. So we've got to convert this a little bit. So we'll worry about the sig figs at the very end here. So we can go from seconds to minutes or straight from seconds to hours, which is my preference. And 1 hour is 60 times 60 or 3,600 seconds. And then there are 24 hours in a day and go from there. So we'll divide by effectively that number we got by 3,600 and divide it by another 24. And we're going to get 366.8 days. So, and number of sig figs we want here is looking like just 2 actually. So we'll round this up to 366 370 days. And this is rounded, you might have guessed. So this is the average distance from the Earth to the Sun, which is why this comes out so close to 365 days. If you have found this lesson helpful, consider giving it a like. Happy studying.